In this explainer, we are going to tear generative AI down to its core components. We're starting with the highest level model types and then drilling all the way down to the fundamental building blocks. And yeah, the critical limitations that really define this technology. Okay, let's dive right in with the most fundamental distinction in all of machine learning. Seriously, this one sets the stage for everything else that follows. It's the two core ways a model can learn from data. So, first up, we've got generative models. The best way to think about these is like a culinary student who learns the entire recipe for a cake. They don't just learn to recognize a cake when they see one. They understand the ingredients, the chemistry, the whole process so deeply that they can bake a brand new, unique cake from scratch. And that's their power, the ability to create totally new stuff, whether that's images, text, or music. Now, on the other hand, you have discriminative models. These guys are the food critics. They don't need the recipe at all. They just need to taste a piece of cake and tell you, yep, that's chocolate, or nope, that's vanilla. They are total specialists in classification and prediction. Their only focus is drawing a really clear line between different categories. And when you lay it out like this, the trade-offs become super clear. Generative models, they're just inherently more complex because they have to understand the entire data distribution. Discriminative models are way simpler and often a lot more efficient for just pure classification tasks because, well, they only have one job: find that dividing line. So, the AI we all interact with every day, from ChatGPT to Claude, it belongs firmly in that powerful generative camp. They create things. So now let's zoom in on the specific engine that actually powers these large language models. An LLM is, at its heart, a highly advanced generative model, but it's one that's specialized purely in language. It's been trained on a truly staggering portion of the internet, so it's learned grammar, facts, different reasoning styles, even multiple languages. And that is what allows it to generate coherent text, answer our questions, summarize documents, and even write code. This was the turning point. Before 2017, models had a really short memory. They just struggled with long-term context in a piece of text. But the transformer architecture, which came from researchers at Google, changed everything with a mechanism called self-attention. This allows the model to constantly weigh the importance of every single word in a sentence relative to every other word, no matter how far apart they are. And that gave these models a vastly superior understanding of context and nuance. But how does a model actually see our language? I mean, it doesn't read words and letters the way you and I do. To get this, we have to go to the most fundamental level, what you could call the atoms of AI language. Just think of tokens as the atoms of language for an AI. Every single prompt you write, every response you get back is first shattered into these tiny little units. A token might be a whole word, like house, or a piece of a word, like gener and additive, or even just a simple punctuation mark. Now, this process is the absolute bedrock of how LLMs work. The model isn't operating on text, it's operating on pure math. The tokenizer is the crucial translator here, converting our words into a sequence of numbers, these token IDs, that the neural network can actually process. This happens on the way in with your prompt, and then the entire process is just reversed on the way out to turn the AI's calculated number sequence back into the words we can read. And this quote from Andrej Karpathy, it just brilliantly illustrates a really profound consequence of all this. So many of the strange limitations we see in these incredibly powerful models, they're bizarre failures at what seem like simple tasks. They're not failures of logic. They are artifacts of this very first step, tokenization. So why can't a seemingly super intelligent AI reverse a simple word like word? It's because it doesn't see WORD. It sees a single indivisible token, let's say token number 5824. It has no concept of the characters inside that token. And the exact same thing is true for arithmetic. It sees the number 52 as just another token, not a mathematical value. The model is a world-class pattern matcher, not a calculator. Okay, so we have our architecture and we have our tokens. Now, how are these massive models actually built? Well, it's not a single step. It's a crucial two-stage process that gives them both their power and their utility. The whole approach is to go from generalist to specialist. First, you have the pre-training phase. This is where a foundation model gets created by basically letting it learn unsupervised from a colossal chunk of the internet. This builds its broad, general knowledge. Then comes fine-tuning.
where you take that powerful but raw model and train it on a much smaller, high-quality data set to specialize it for a specific job, like being a helpful chatbot.
And the difference in scale here is just staggering. Pre-training is this monumental, multi-million-dollar effort that really only a few giant tech companies can even afford. That's what creates the raw engine. Fine-tuning, though, is way more accessible. It's the process of taking that raw engine and installing the specific controls to make it a helpful, harmless, and useful tool for a very specific purpose.
So we have our model, but this architecture, which has been trained on the messy, chaotic reality of the internet, it has inherent flaws. So let's tackle the most notorious and potentially the most dangerous limitation of all: hallucinations. It is so crucial to understand that a hallucination isn't a bug in the traditional sense. The program doesn't crash or throw an error. Instead, the model confidently and often very eloquently presents completely fabricated information as if it were a verified fact.
At its core, this comes right back to token prediction. The model's number one goal is just to generate the most statistically probable next token to create a coherent sentence. Its goal is coherence, not truth. So if a made-up story sounds more plausible than a complex truth, the model might just choose the fabrication. It's what some people call a stochastic parrot. It's brilliant at mimicking linguistic patterns, but it has zero grounding in reality or meaning.
And this shows you just how high the stakes are. In fields like law, or medicine, or finance, where accuracy is absolutely non-negotiable, a convincing fabrication can have disastrous consequences. The model isn't being malicious. It's simply executing its core function, completing a pattern, without any connection whatsoever to what is actually real. By peeling back all these layers, from that high-level distinction between generative and discriminative models, down to the transformer architecture, the weird quirks of tokenization, and the very real problem of hallucinations, we can finally start to move past this idea of magic. This mechanical understanding is what empowers us to be more effective, more critical, and ultimately more responsible users of this incredibly powerful technology.